So, good morning, good afternoon, or good evening, wherever you are in the world. My name is Stephen Waldron. I'm Local Product Line Manager at Vector in our UK subsidiary. And welcome to our webinar today, Introduction to AUTOSAR, where we will spend the next 45 minutes to an hour talking about the basic principles of AUTOSAR. At any time in the webinar, if you have any problems with the audio or similar related issues, please use the chat window, and this will inform our hosts of the issue and they can help you resolve this. If you have any technical context-related questions, please use the Q&A window. I have a colleague standing by who will answer the questions for you, and at the end of the webinar, we will choose some of the most interesting and pertinent questions, and my colleague Oliver will talk through those questions for the benefit of the whole audience. So thank you for your attendance today, and let's get into it. First of all, I want to introduce some of the topics of the drivers of AUTOSAR, what's helped introduce AUTOSAR into the automotive industry. Then I want to talk about the technical content of AUTOSAR from both a bottom-up and top-down point of view. And then I want to just briefly introduce some of Vector's solutions to the AUTOSAR problems. So let's get into it. Why AUTOSAR? Well, of course, over the last 20 or more years, we have seen the electrical and electronic complexity and the physical amount of software within the vehicle growing very, very quickly. So software within vehicles really started back in the mid-1970s with the first ECU, a Bosch ECU for engine control, cruise control and fuel injection timing. Nowadays, the engine electronic control unit, the engine ECU, has more or less become mandatory in order to meet today's stringent emissions legislations. But along with the proliferation of the engine ECU, there have also been many other ECUs brought into the vehicle. For example, the transmission control unit for gearbox control, a braking ECU for ABS functionality or traction control. And these ECUs all talk to over various network systems and network communications, and typically that communication might be something like CAN, Controller Area Network. Nowadays, we see multiple CAN networks, perhaps 5 or 6 CAN networks on the bus, with many, many ECUs all sharing data between them. And these ECUs can take advantage of the data that's effectively public data published onto these buses to provide new features and new functions. So whereas before we had cruise control, perhaps now there's radar information on the bus, and just as a software function alone, you might be able to implement something like adaptive cruise control. As the years have gone on, the number of features within the vehicle has grown exponentially. And really, the features today on the vehicle, the software features within the vehicle, are really the differentiator between a high-end vehicle and a low-end vehicle. We see that 80% of the newest innovations on the vehicle today are based on software functions. Features like lane keep warning or lane keep assist function, automatic parking systems, adaptive cruise control systems, adaptive headlighting systems, automatic software updates. These are all new features that are saleable features of the vehicle, and really differentiate the high-end vehicles from the low-end vehicles. When we take a look at the development of the technology inside the vehicle, it used to be that these systems used to be based on single electronic control systems. You would have a transmission ECU or a engine control ECU or a ABS braking ECU. Today, the ECUs don't so much work autonomously, but rely more and more upon the data from other ECUs in order to fulfill their vehicle function. For example, a very complicated system like lane departure warning systems or lane keep assist systems would rely upon multiple sensors from multiple ECUs within the vehicle. And as we see this move into the future, into the realms of 2020, we see more and more complicated electronic networking being involved for car-to-car communications or car-to-grid communications. When we look at the technology inside the vehicle that's put in place to support these infrastructures, we can see that nowadays a high-end vehicle will have up to or more than 100 ECUs, electronic control units, all working together harmoniously in order to deliver these vehicle functions. Bus technology has moved beyond CAN into the realms of FlexRay or Ethernet or perhaps even CAN FD in the very near future. And the processing power inside the actual ECUs themselves has evolved from 8 or 16-bit controllers to nowadays 32-bit controllers are more or less commonplace, perhaps even 64-bit or more commonly dual-core or multi-core 32-bit architectures. So as the vehicle functions have increased, so the electronic complexity and the power of the processing inside the vehicle has also had to increase. And the scope of AUTOSAR really covers this area in the middle, complicated electronic control systems within the vehicle. So this is the area of scope for AUTOSAR. What challenges face AUTOSAR today? Well, this is some of the challenges that the automotive OEMs and their Tier 1 suppliers want to overcome. The E&E complexity is growing very fast. That's electrical and electronic complexity. There's more complicated components, there's more complicated bus systems, there's higher complexity of the microprocessors. And driving all that, the physical amount of software we have, the quantity of software we have is exploding. So the number of code lines we have inside the software is increasing at an exponential rate. Many, many different hardware platforms have to be supported. If you go into your local computer shop and attempt to buy a new PC, it might be that you have a choice of 10 different processors to choose from, if you're lucky. But in the automotive industry, we have hundreds, if not thousands, of different microcontrollers and their derivatives to support. And all the different OEMs and their Tier 1 suppliers, many use different development processes and exchange data formats in various different ways. And all of this is not harmonious for developing systems in a very efficient way. So the main objective of AUTOSAR is to improve the overall efficiency, essentially with a message of reuse, reuse, reuse. We want to reuse software not only across different car lines within the same vehicle manufacturer, but also across the OEM boundaries. And this means the different OEMs are all reusing the same software inside their vehicle. Reuse of the different development methods and tools. So we're all following similar processes and similar development tools for developing the software. And reuse of what's termed in AUTOSAR the basic software. This is the software underneath the application within the ECU itself. AUTOSAR stands for Automotive Open System Architecture, and it is essentially a partnership. It's a partnership between the car manufacturers, their Tier 1 and Tier 2 suppliers, other companies in the electronics industry, semiconductor manufacturers, and tool software vendors within the industry. It has a common principle: cooperate on standards and compete on implementation. And this means that we're all writing software to the same standard, but now we compete on areas such as price, lead time, quality of the software, time to market. But essentially, the software itself is all written to one common standard. The AUTOSAR partnership now consists of just over 200 members, and so far more than can be shown here on this diagram today. It consists of various different levels of membership, starting with the core partners that you see here on the left-hand side, and they're essentially the founding fathers of the AUTOSAR partnership. Outside of that, you have the premium members, which includes Tier 1 suppliers, software suppliers like Vector, shown here on the slide, tool and service providers, and the semiconductor members. And then around the outside, associate members and further attendees. From the AUTOSAR website, www.autosar.org, you can go on and see all the AUTOSAR members, and today I had a look and you can see over 200 members actively participating in the AUTOSAR partnership today. AUTOSAR is a growing and evolving standard, and some customers I speak to say, well, AUTOSAR, it's not finished, and you could say that that is true, and it's because it's an evolving standard, always encompassing the latest developments in the technology today. In 2007, when we were at AUTOSAR 3.2.1, we were just a little over 8,000 pages in the standard, and that came up to about my waist. But today, at AUTOSAR 4.2.1, we're touching upon 20,000 pages within the AUTOSAR standard, and this just comes above the top of my head now. Far, far more than anyone can ever understand for one person. If you go onto the AUTOSAR website, this is an open standard, so you can view all these specifications and documents, and very often it can be quite daunting to see so much, effectively so much paperwork and so many lines of requirements. But let's have a little bit of a look, a bit of a brief overview of what these standards encompass. So I want to look at AUTOSAR from a two-pronged approach. First of all is the bottom-up approach, and the bottom-up approach looks at the basic software architecture underneath. So first of all, AUTOSAR defines a layered architecture for the software. This means it structures the software in a layered way to abstract away from the hardware. This is the structure of the basic software underneath. Now, the basic software consists of just a little bit over 140 different software modules. But here we can see just some of the most common ones encompassed in Vector's basic software stack. I want to start over here on the left-hand side, and we have a look at the operating system. So you can see the operating system essentially runs all the way from the top up at the application level, right down to the bottom, down to the microcontroller. The reason the operating system runs right from the top all the way down to the bottom is that it has to interface to both the application layer and the microcontroller itself. It has to schedule timers on the microcontroller and configure interrupt service routines, and hence it has an interaction down at the hardware layer, but also it has to schedule application tasks, and so it touches right up at the top, up at the application layer. Moving along to the bottom, we have this layer called MCAL, and MCAL stands for Microcontroller Abstraction Layer. This might also be known as low-level drivers or hardware abstraction layer or device drivers, and it's essentially the layer of software that touches the microcontroller peripheral registers. So we have common drivers like the ADC driver, the EEPROM driver, the CAN driver, and for mostly every peripheral on the microcontroller, you will find a microcontroller abstraction layer piece of software. And this is to present the basic software above with a common API to access the hardware and provide common access and common functions for the hardware, regardless of the hardware implementation underneath. Typically, the MCAL layer will be provided by the silicon vendor. So, for example, if it were an Infineon processor, you would source the MCAL software for Infineon. A Freescale processor, you would source the MCAL software from Freescale, for example. Vector's basic software sits on top of these MCAL drivers, and I want to take each one of these parts of the stack one by one and introduce them. So first of all, we have the system drivers, and the system drivers encompass things like the BSWM, the Basic Software Manager, the ECUM, the ECU Manager, the Watchdog stack, the Watchdog interface, and the Watchdog Manager. And some of these modules are responsible for setup of the ECU and configuration of the state of the ECU, and essentially to get the ECU up into a running state. Further along the line, we have the diagnostics modules, DCM and DEM, that's Diagnostic Communications and Diagnostic Event Manager, and FIM, Function Inhibition Manager. I don't have time in this webinar to cover every single module within the stack, but hopefully I will give just a brief introduction to the most important modules. Underneath this, we have the AMD modules, and this is for AUTOSAR monitoring and debugging. This part of the software runs above XCP and allows you to view and debug the internal variables of the AUTOSAR stack prior to production. Next along is the memory stack, and in here we have EEPROM abstraction, flash EEPROM emulation, memory interface, and NVM, the non-volatile memory. So of course there's often a high dependency on the diagnostic modules, on also the memory interface as well, because when diagnostic events occur, those have to be logged into memory. And so the specifications are written in such a way that there's often a dependency between two parts of the stack. The diagnostic modules place calls upon the memory modules, and those memory modules have to work in an AUTOSAR way and are expecting AUTOSAR type calls from the diagnostic modules. Next along, we have the communication modules. And starting here with CAN, we have things that may be familiar from Vector's CAN-embedded days. Functions like CAN network management, CAN interface layer, CAN state manager, and also XCP on CAN. Then we have communication stacks for LIN, so a similar configuration for the LIN stack, and also FlexRay communications and Ethernet communications for automotive Ethernet. There's another layer above here again called the COM layer, and the COM layer's functionality is to abstract away from the physical bus. And this means that in AUTOSAR you have a concept called the PDU concept, a protocol data unit. The application, when it looks at sending and receiving data, only looks at the sending and receiving of a PDU, a protocol data unit. And in this way, the application doesn't have to have visibility of the physical network bus underneath. The application can send and receive PDUs, and it's a different task in the workflow to actually map that PDU down into a physical communication parameter, and that task is called data mapping. So the application can be developed more or less independent of the physical bus underneath. No longer is the application sending a CAN message or receiving a FlexRay message. It's sending or receiving a protocol data unit. And it's the task of the integrator who takes that communication stack and places that stack on the actual ECU itself to determine whether that PDU is mapped to either a CAN message or mapped to perhaps a FlexRay message. And in this way, the Tier 1 can develop his application independent of the OEM's bus and whether OEM A works on a CAN bus or OEM B works on a FlexRay bus, for example. Then we have some I/O drivers, and I/O drivers essentially interface to the ADC driver or the ICU driver, for example. We have library functions for calculating CRCs or providing end-to-end protection. And then we have a small area here called the complex drivers. The complex driver I like to think is a little bit of a get-out clause. If anything isn't quite defined within AUTOSAR, or if anything needs to access the hardware very, very quickly from the application down to the microcontroller without going through the entire layers of the AUTOSAR stack, then it can sit here as a complex driver. So technically, for example, an I2C driver may sit in here as a complex driver because I2C functionality is not formally defined within AUTOSAR. So in the strictest sense, an I2C driver would sit as a complex driver. Now I want to move up to the RTE layer, the layer you see here in between the basic software and the application software. RTE stands for Runtime Environment. And it's the layer of software within the AUTOSAR architecture that is wholly generated by the configuration tools. It's the wholly generated layer of software. And it provides an abstraction for the application away from the basic software underneath, where the basic software is very much tied to the hardware implementation, but the application is abstracted away from that hardware implementation. And somewhere down the chain you have to marry those two up, and how you marry them up is with the generation of the RTE, the Runtime Environment layer. Within AUTOSAR 4, the Schedule Manager has moved out from the sys layer in here into the RTE layer, because the Schedule Manager is responsible for generating the task ticks into the application, so the application can schedule its tasks. And so this is part of the software that's also automatically generated in conjunction with the RTE. So this is just a very brief overview of the AUTOSAR architecture from a bottom-up point of view. And if you go onto the website and look at the many, many, many specifications, the 2 meters high of specifications, this is the view you will have of AUTOSAR, is the many, many specifications all defining the functionality and the API and the content of these modules. But there's also another view of AUTOSAR which is not so well known about and not so well published on the AUTOSAR website, and that's the top-down view of AUTOSAR. This is really, what do the OEMs want to get out of an AUTOSAR architecture? And why do they want to impose this rigor of layered software architecture and abstraction and complexity of generating an RTE? And it's because the OEMs want to start designing vehicles very much from a function-centric point of view rather than an ECU-centric point of view. From the OEM's point of view, they want to sell features in their vehicle. They want to put features on such as adaptive cruise control, lane keep assist system, and really they're not quite so worried about how many ECUs are on the vehicle or what ECUs do which function, but they're just essentially interested in putting those functions onto the vehicle in the first place. So AUTOSAR has a concept for designing software in this way, and essentially it starts with the software requirements. So we have a requirement for a new feature, and I always like to use an example of tyre pressure monitoring. In the UK, tyre pressure monitoring became mandatory as of 2014, and this means that any OEM designing a new vehicle has to put tyre pressure monitoring into that vehicle. This potentially means adding more sensors and yet another ECU into the vehicle. But we have many, many ECUs in the vehicle already, perhaps 100 or more ECUs. And there are ECUs everywhere within the vehicle, in the roof, in the floor space, in the doors. So adding a new ECU means more weight, more wiring harness, more load on the bus, and it's additional cost that the OEM wants to minimize. How do we put that function of tyre pressure monitoring onto the vehicle whilst also minimizing the number of ECUs we have in the car? We start with the requirements. And from the requirements, for example, we have requirements for tyre pressure monitoring, we can map those to functions or features. So we have the tyre pressure monitoring feature, the ABS feature, the lane keep assist feature. And then, when we know some certain characteristics about those features and functions, we can map those features and functions to the already existing ECUs within the vehicle. And in such a manner, if we have tyre pressure monitoring, for example, designed in an AUTOSAR way, that means, theoretically, the TPMS software can be hosted on, for example, an ABS braking unit, where the ABS braking unit is capable of hosting AUTOSAR software components, but also has some spare capacity and the necessary inputs and outputs. And using this methodology, we can think about designing our vehicle using AUTOSAR in a more function-orientated way rather than a more ECU-orientated way. This is the old methodology we used before AUTOSAR. Before AUTOSAR, we would very much specify the vehicle in an ECU-centric way. We would have a number of ECUs in the vehicle. These ECUs would all communicate with one another through CAN messages or through 5X messages. And really, if we look at this from CAN, we used to think of this as the DBC file was the center of all things. The DBC file would define the number of ECUs you have in the vehicle, the messages that they send to one another, the signals within those messages, and that DBC file would form the basis of the communication software within each ECU and how the application behaved, using the messages as the starting point of how the ECUs communicated with one another. An AUTOSAR workflow works very different to this. So in the AUTOSAR workflow, we think about the software, we think about the SWCs first, the software components first. The software components are the actual parts of the software that perform the vehicle function, the vehicle feature that we want to achieve. And we can think about how we want these software components to work together and communicate with one another before we even start thinking about ECUs or buses or anything that's hardware related. So we can start by defining the entire vehicle architecture just in terms of software, software components, and how they communicate with one another between. And in AUTOSAR, we use this conceptual thing called the virtual function bus, the VFB. The VFB is an imaginary, if you like, an imaginary bus where communications between the software components are passed. So, for example, the tyre pressure monitoring system may pass a message to the instrument cluster if the tyre pressure is low. At some point in time, actually relatively quickly, we want to map those software components down to already existing ECUs within the vehicle. So here, let's take our TPMS example as a good example. ECU1 might be the braking ECU. ECU2 might be the instrument cluster displaying the warning symbols. And within the software component 1 might be the ABS software that flashes the ABS light in the case of an ABS instance. Software component 3 resides on the instrument cluster and actually flashes the light on the instrument cluster. And here in this example, we can add in software component 2, the tyre pressure monitoring system, into the already existing ABS ECU. And of course, the additional message that flashes the TPMS light on the dashboard also has to be supported through the communication parameter. But again, in this instance, we haven't really thought about, is it CAN, is it FlexRay? That's not typically quite so important at this point. When we've allocated the software components to the ECUs themselves, we create something in AUTOSAR called the system description. And the system description is an AUTOSAR XML file for describing the makeup of the entire system, the entire vehicle architecture in terms of ECUs and the software components within. And from that, of course, the OEM has to hand some information down to the Tier 1. And the information they provide is called an extract of the system description. And the extract would be the information simply concerned with one ECU. So the ECU supplier knows what ECU they are, which bus they reside on, and what software components reside within that ECU. And finally, from the extract of the system description, we can create a detailed view of the software inside the ECU. And this detailed view is called the ECU configuration description, or the ECUC file. The ECUC file contains descriptions of the software components inside, information necessary for generating the RTE, and the basic software required underneath to support those software components. So that was AUTOSAR from a top-down point of view, and I just want to speak very briefly about the usage of AUTOSAR throughout the automotive industry. So within Vector, we have quite some good visibility of different OEMs and different Tier 1s and how they use AUTOSAR, and that's often of interest to many customers and people. And I want to look at the different aspects of AUTOSAR and how it's being adopted. So AUTOSAR from a bottom-up point of view, the use of the basic software and generation of the RTE. We find that today that's being very well used across the European OEMs, and we're starting to see more and more use within the USA and Asia. We think that as of about 2017, the AUTOSAR architecture aspects will be very broadly used globally across the automotive industry. When it comes to the data formats, and this is essentially the replacement of the DBC file with AUTOSAR system descriptions or ECUC files, today we find that only a few OEMs are very strongly using the AUTOSAR extracts and the AUTOSAR communication descriptions, but more and more OEMs are steadily migrating away from DBC files and 5x files and moving towards the AUTOSAR AR XML files. And we really think this will be a standard method of data exchange from around about 2020. Possibly the most complicated aspect of AUTOSAR are the development methodologies. The replacement of an ECU-centric design with a function-orientated development, where you develop your software components and allocate them to the already existing ECU architecture within the vehicle. So far, nowadays, we see many OEMs that are distributing software components, but this is really just a stepping stone towards the full function-orientated development, and we really think that fully function-orientated development will only become standard really following on from 2020. There are many pushes that push the OEMs and the Tier 1s towards AUTOSAR. Perhaps the requirements for functional safety, ISO 26262, the introduction of new bus technologies such as FlexRay or Ethernet. These are all pushes that encourage an OEM or a Tier 1 to move towards an AUTOSAR architecture that support these new types of technologies. But there are also hurdles and legacy issues to overcome. So some OEMs may have existing network management issues that they have to resolve, or they have legacy problems with existing data formats that they can't replace. We have a fairly good view of all the different OEMs and their different migration to AUTOSAR. AUTOSAR really is not a one-hat-fits-all. Different OEMs, for example, have adopted AUTOSAR at different times. So those OEMs that were early adopters of AUTOSAR are perhaps still using AUTOSAR 3, or perhaps migrating on a migration path from AUTOSAR 3 to AUTOSAR 4. Nowadays, any OEM that is a new adopter of AUTOSAR would probably jump straight into using AUTOSAR 4. And the scope of how much of the AUTOSAR standards they use is different as well. Some OEMs only use it for the communication descriptions, perhaps only CAN and LIN and the communication stack itself. Some OEMs will use it for a complete adoption of all the bus network systems. Some OEMs are still using DBC files and LDF files or FIBEX files, the old format of description of the communication, whereas some OEMs have moved fully over to system descriptions or extracts of system descriptions. And some OEMs are very keen on using the basic software and perhaps the RTE above, but are not so interested in developing software components, and other OEMs have taken on the adoption of software components and basic software. So essentially we see that although AUTOSAR is one standard, inside there are differences in functionality between the AUTOSAR 3 and AUTOSAR 4 standards. There's differences in the data and workflow that the OEMs and the Tier 1s are using, and whilst it's one standard, it's a one standard with variations, and so there are variations inside that we have to support. When we look at the market, we definitely see that the number of OEMs using AUTOSAR is growing, the number of Tier 1s taking on AUTOSAR is growing in order to support their OEM customers. The functionality inside AUTOSAR is growing. In the last couple of years, we've seen inclusions of ISO 26262 and Ethernet within the AUTOSAR 4 standards. The investment of tool providers to support AUTOSAR with their tooling is also growing. And perhaps most interestingly for me, alternative solutions are losing ground. So it's more common the case nowadays that we see that the only solutions that are available are AUTOSAR solutions. And we see a growing market, growing at perhaps 25% a year. I hope that was some interesting broad background to the AUTOSAR problem, and now I want to present some solutions. And I want to present some solutions in the form of Vector's products and services in the AUTOSAR market. So we have a full end-to-end solution for AUTOSAR, moving right up from the left-hand side of the V model from whole system design all the way to the testing tools at the bottom end. And I want to spend a little bit of time just to introduce each solution individually. First of all is our prevision tool. And our prevision tool is mostly aimed at the system design of an entire vehicle or ECUs networked within the vehicle. It allows you to create software components and map those software components down to ECUs. It allows you to create an architecture for the ECUs and create system descriptions and extracts of system descriptions. But of course, not only does it support AUTOSAR, but it also supports various other architectures beyond AUTOSAR as well. Moving slightly down the chain, we have our DaVinci Developer tool. Our DaVinci Developer tool I really think is world-class, and it's for the creation of software components in a graphical manner. You can create the software components, you can create runnables inside, you can create ports and interfaces, the way that the data is communicated between software components. You can define the internal behavior of the software component, and in AUTOSAR this is called runnables. And a runnable is essentially a software function within a C file. So a runnable would map exactly to a C function. You can perform consistency checks across the software components to make sure at pre-compile time that they would interact in the right way. And then you can perform activities known as data mapping and task mapping. Task mapping allows you to map the runnables into the operating system to ensure that all your runnables are called on time and in the correct tick cycle. And data mapping is where you map the internal data within the software component, how the application sees it, as PDUs, to real CAN signals or real FlexRay signals. DaVinci Developer is really the tool of choice for developing software components at the application level above the basic software. When we get down to the basic software underneath and the configuration thereof, the tool that we use is called DaVinci Configurator Pro. And DaVinci Configurator Pro can view or configure not only our basic software, but also third-party basic software such as the MCAL drivers. We can make certain configuration settings to enable the features in the hardware or disable features in the hardware. And together with DaVinci Developer and the basic software configuration, these two tools together allow you to make up an entire working basic software stack and corresponding application. When it comes to testing, back up the other side, it might be that you want to test on a virtual target prior to actually running your software on the ECU. And for this, we would use our virtual test target tool that's currently in planning, a development feature. The virtual test target allows you to switch easily and conveniently between a real MCAL for a real MCU and the virtual integration platform, essentially an MCAL built for the Canoe tool. So you can run the same basic software and configuration on the Canoe system, and when you're ready to switch to the real ECU, you can switch out the Canoe MCAL, switch in the real ECU MCAL, and away you go on real hardware. Finally, of course, we have our Canoe tool, which is very well known in the industry, so I don't want to spend too much time introducing Canoe particularly, but I want to highlight its AMD feature, AUTOSAR monitoring and debugging, which, if supported by the basic software modules underneath, allow you to debug and monitor in real time the internal variables of the AUTOSAR basic software stack. So, our ECU Tier 1 customers have many requirements, and here's our solution. First of all, of course, they want performance and they want high-quality software. They want to be able to use one set of software, ideally for multiple OEMs and multiple projects. They want to plan reliably. They want to know how long it's going to take to deliver a project and at what cost. So they need to be able to cost effectively, but also get value for money inside his project. And this is how Vector tries to answer. We like to provide our customers with very powerful tooling. Really powerful configuration tools such as the DaVinci Configurator and the DaVinci Developer that give you nice comfort graphical user interfaces with diff and merge automation. We provide optimized code with certain pre-configurations inside. From Vector, you get what's termed a SIP, a software integration package, which is a pre-tested configuration of software according to your requirements that you know is effectively working out the box. And it's a mature product. We have over 20 years of experience of developing embedded software, over 1,200 person years invested, and many AUTOSAR projects delivered. Currently, we're working to standards such as Automotive SPICE Level 3, and certain components have conformance to ISO 26262. To address all our customers' projects, we have AUTOSAR solutions for multiple OEMs. We also support many different microcontrollers. So Vector attempts to remain microcontroller agnostic, if you like, and as long as the microcontroller is supported with an MCAL, a microcontroller abstraction layer, we will support that microcontroller. We support many different functions inside, even the newest technologies such as CAN-FD, FlexRay, Ethernet, perhaps even J1939 standards within the AUTOSAR stack. And we have many different types of software integration package, many different types of SIP available. Evaluation SIPs, prototype SIPs, all the way through to production SIPs, fully validated and fully tested, ready for production. Customers want to plan reliably, and this means we provide an upfront specification. We spend a lot of time at the requirement stage working through a detailed questionnaire with the customer to make sure we've included all the modules he will see necessary in his AUTOSAR stack. We attempt to offer turnkey deliveries with defined delivery dates tested on real target hardware. And Vector has a strong policy of no hidden costs. We try to capture all costs up front at the start of the project, so it's very clear to you how much the project is going to cost over the course of the years of the project. We also offer scalable licenses, and this means you only need to license what's needed. Perhaps you only need prototype licenses, or maybe all the way through to production. And in that way, we can offer long-term benefits. And we like to reward our customers also with discounts when they come back and they use Vector time and time again for their basic software. We have a discounting model for multiple projects. We believe our offering for AUTOSAR is unique around the world. So, in a nutshell, it's a challenge. AUTOSAR is very beneficial, brings many benefits to address the complexity already in the automotive industry, but it's a challenge to introduce. It's good to have mature equipment and experienced guidance, and we think with partnering with Vector for your AUTOSAR projects, you'll get this. Many customers become very daunted about introducing AUTOSAR. They say it's complicated and perhaps expensive. But my argument to this is that the complexity is there already. AUTOSAR is not really the problem. The problem is the inherent complexity in the architecture itself and the technologies involved in the automotive industry today. AUTOSAR is not the problem of this complexity. It should be viewed as the solution. AUTOSAR is the tool to manage this complexity. I hope this webinar has been of some interest to you today. There are many free resources available on the Vector website in order for you to learn more. We have different e-learning sessions that you can take place in. There are many other webinars with more detail on various parts of the AUTOSAR stack or AUTOSAR solutions. And there's more general information about, in particular, Vector's AUTOSAR solutions. So please visit vector.com and search for AUTOSAR. And for any of your AUTOSAR needs, you should find a solution from us. So thank you for your time today. In the meantime, my colleague Oliver Garnatz has been fielding your questions and answers, and I'll hand over to Oliver now. I'll ask Oliver to select some of the most interesting Q&As that he's been addressing today, and perhaps talk about those with you for the next 10 to 15 minutes. Thank you, my colleague Oliver Garnatz.
Hello, my name is Oliver Garnatz, and here are the most interesting questions. In order to start with AUTOSAR, how would be the best way? For sure, the best way is a free of charge e-learning on our homepage. You can just start with them. To join one of our training classes would also be a good idea. And if you have further project-specific needs, then please contact us, because then we can for sure help you to get into AUTOSAR or to support your different projects. Next question was, who will provide software component descriptions and system descriptions? Software component descriptions describe the functions itself, so all the interfaces, the behavior of the function towards AUTOSAR. Therefore, the function developer is the guy who needs to also provide the software component description, similar then to a header file of a C module. The system description is the file describing all the communication, the dependencies for the whole vehicle. So therefore, the vehicle manufacturer should provide a system description. Till now, not all vehicle manufacturers provide the system descriptions, but more and more will do. They provide typically an ECU extract of the system description, so just focused on your personal ECU then. And for sure, also many vehicle manufacturers provide legacy files like DBC, FIBIX, or LDF files. Then I was asked about the support of J1939, which is also a protocol used in the heavy-duty and agriculture industries. This is meanwhile also supported in AUTOSAR. AUTOSAR is also heading to support the heavy-duty industry more and more. Here, the typical use cases for Chain39 ECU is meanwhile supported with AUTOSAR. You can build your applications to also with the Chain39 ECU. What's also supported a mixture between the classical communication patterns and the Chain39 communication pattern. So also here you find good functionalities. As extension to AUTOSAR, we meanwhile also provide the isobus support to support more the agriculture industries, having here extensions to the Chain39 protocol. Also very often is the question about how to handle the safety applications. For sure, AUTOSAR is designed to support safety. Different measures can be used for that. Memory partitioning for sure is the first, most important to guarantee the freedom of interference. EGE communication to communicate through black channels like a CAN network or something else is also supported. Individual partitions with some functions inside could be restarted to have a fail operational system support. And in the documentation areas also you can do a lot of safety annotations in your software component descriptions in the system templates to assign here different safety requirements to have here better documentations. So that was the most important questions. I give back to Stephen.
So thank you very much, Oliver, for addressing those Q&As that have been raised through the course of the webinar. We will stay just a few more minutes on the line for any further questions. If you have any questions for myself or Oliver, please raise them in the Q&A window, and we'll address them over the next few minutes. Thank you.